Hey everyone, in this video we're going to be talking about perimeter and area. So we're going to be talking about a few different shapes here. We're going to be talking about rectangles, triangles, parallelograms, trapezoids, and circles. Okay, so to begin, let's talk about the perimeter of an object. So perimeter, first of all, is a one-dimensional measure. So what do I mean by one-dimensional measure? Well, when we have a perimeter, the units that are going to be on the perimeter are going to be to the first power. Okay, so units will be raised to the first power. Okay, now contrasting this with area, area is considered to be a two-dimensional measure. Okay, so the units will be raised to the second power in the case of area. But let's still talk about perimeter here. So I have this object here. It's this block here. It's almost like a little Tetris block. We see that the outside edges are labeled with some units here. We have 13 feet, 14 feet, and so forth. So the perimeter of an object is going to measure the outside distance, or the distance along the outside of the figure. So in this case here, the perimeter, we could just abbreviate with a large P here. The perimeter is going to be, and let me drop the units for now, but the perimeter will be, we're going to have 13 plus 14 plus, now up here we have 6 feet is the distance here, and then 9 feet along that side, plus 7 feet, then plus the remaining 5 feet. So what do we get? So 13 and 14, we get 27. This would be 33, and 42, 49, and 54. So we're getting 54 feet for the perimeter of this object. Now it doesn't matter what the object happens to be, the perimeter is still going to be the distance along the outside edge of whatever figure I happen to draw. Okay, in this case it was this block here, so you just measure up the outside edges. Now, again, the perimeter was a one-dimensional measure, right? So it measures the distance of these lines in the figure, essentially. Now this is different from area here. Area is a two-dimensional measure. Actually, wait. Let me go back to perimeter here. Yeah, when I wrote my units here, 54, and the units on 54 were feet, and feet here is to the first power. Right? When it's to the first power, we could omit the 1, but again, perimeter is the one-dimensional, so our units here are to the first power. Now, going back to the area, so area is a two-dimensional measure. Okay, so what this means is that we're measuring a space in two different directions. Okay, so two-dimensional measure, so this means that whatever units we're working with, units will be raised to the second power. Okay. So let's take a look at this first figure here. Now, finding the area of an object is finding the space within the object, okay, within the enclosements that you happen to have. Okay, in this case, I have a rectangle here. Now, the area is basically synonymous with, in this case, counting the blocks inside of this figure. Okay, now you could see that it's 3 blocks down and 4 blocks across. I'm considering these blocks to be 1 centimeter by 1 centimeter. So this whole side is 3 centimeters and this whole side is 4 centimeters. Now, if each block is 1 centimeter by 1 centimeter, the area of the block is considered to be 1 centimeter squared. Or, if you're taking a physics course or something like that, I think you may be yelled at if you call this 1 centimeter squared. The way that you may want to say this is 1 squared centimeter. Okay, it doesn't matter to me how you say it, 1 centimeter squared or 1 squared centimeter, that's fine. Now, of course, you write the squared after the centimeter, but you should still probably read it as 1 squared centimeter. So that's the area of one of these little blocks here, just a squared centimeter. And when you add up all these blocks, now how many blocks are inside of this figure? We have 12 blocks, so we're going to say A is equal to 12. All right, we have 12 blocks. Now the units, I have centimeters, right? But centimeters here, if I just write it like that, that's a one-dimensional measure, okay? That's like the distance along a line. This is a two-dimensional measure, meaning we need to have the squared sign up there. Okay, so never forget, when you're dealing with area, if you have units, sometimes in math, we may not have units, but when we do have units, those units are going to be squared. So we would read this as 12 squared centimeters. Now, in the case of the second figure here, I have another sort of Tetris block here. I have that these blocks are 1 foot by 1 foot. This means that the area of this block here is going to be 1 squared foot. So the space inside this block is 1 squared foot. So if I want to know the area of this figure here, again, finding the area is synonymous with counting the blocks inside this figure. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? So the area is 14 squared feet. Okay. Now, even though I say it's squared feet, you don't put this square in front of foot. It's always going to be after here. Okay. Now, if that's the case, if counting the blocks is synonymous with finding the area, you may see that there's a shortcut to find the area here. Well, if we just did this outside edge here multiplied by this outside edge here, so this would be 3 centimeters times 4 centimeters, you'll see that we're going to get 12. That's 3 times 4. And then centimeters times centimeters. Well, we have not talked about exponent rules yet, but centimeters times centimeters, since we have something multiplied by itself 2 times, that's centimeters squared, right? So that's why we're getting these squared units here, because essentially we get these areas through multiplication, and multiplication between these units will yield square units. In the case of our second figure here, we may have to be a little bit more clever to get the area. If we take a look at this, let me try to draw some lines around here. So if we take a look at this first rectangle, this is 2 by 4, right? So this would be 2 feet times 4 feet. So that's the area of my first figure. And then we would need to add in this second figure here. Okay, so 2 feet times 4 feet. Now this one is going to be 2 times 3 to get this area here. So that's 2 feet times 3 feet. And this part here, 2 times 4, we get 8 squared feet plus, and then 2 times 3, we're going to get 6 squared feet. Now this introduced some order of operations too. Oh, well, let me finish the problem here. 8 plus 6, we get 14. And in this case, when you add things together, we keep whatever units we have on there. Like if you add 1 foot and 1 foot, we're going to get 2 feet, right? The units don't change through addition, but they will change dimension through multiplication. So 8 plus 6, we get the 14, and feet squared plus feet squared is still just feet squared, or squared feet. Okay, so either way, we're going to get 14 squared feet here. And yeah, as far as operations go, order of operations, multiplication is going to come before addition. Okay, but we'll be talking about that in a later video. Okay, so that's the major difference between perimeter and area, this one-dimensional measure and the two-dimensional measure. In the case of perimeter, that's the distance along the outside of the object, and the area is the space within an object. Now, depending upon the figure that you're working with, there's going to be different strategies to obtain the area. For the most part, perimeter is fairly simple to get. You just add up the outside edges. So let's go ahead and take a look at a rectangle. Okay, so here I have a rectangle. Now the perimeter, if I wanted the perimeter of this figure, we would need these outside edges here. Okay. Now the rectangles have a width. Let me call this W. Let me actually just label it width. And no, actually, it doesn't matter which side you call length or width, but I'm in the habit of calling the longest side of the rectangle the length. For no particular reason, really. I mean, you could still call it the width. That would be fine, but I like to call the longer side the length, if there is a longer side. And I like to call the shorter side of the rectangle the width. So we have a length and a width of our rectangle. So the perimeter, okay, so this is going to be also the width, and up here is also going to be the length. Now width, you could abbreviate it with a W, and typically for abbreviating the length, I just call it a cursive L here. So the perimeter of a rectangle is just adding up the outside edges. In this case, we want to add up the width, and we have a width over there, so W plus W plus, and then we have a length here, and then a length up there as well. So W and W, we're going to get 2W. In the case of the L's, we get 2 L's. So these are called like terms, and when we add like terms together, what we're doing is we are adding something called the coefficients. But that's also a topic for a later video, so don't concern yourself too much with that at this point. So if you wanted a formula for a rectangle, this would be it, but really just add the outside edges and you'll have it. And as we saw with the block scenario, if you wanted the space inside of a rectangle, you could multiply the width times the length. Okay, so let's say the area is going to be the length times the width, and that's going to give you the space inside of the figure. Okay, so that's for rectangles. Now let's see if we can find out what the area of a triangle is by using the fact that we know the area of the rectangle. So here is a triangle. Now triangles come in many different forms and sizes and shapes. This is one example triangle you may see. They don't all look like this, but typically you could find a base of your triangle. Now you could consider any side of your triangle to be the base. Okay, it doesn't matter which one you call the base. In certain scenarios, it may be easier to call one side the base over another, but that takes experience in looking at multiple different triangles. And the height, I have this labeled H. The height is going to be a perpendicular distance from the base to the highest point in the triangle. Okay. Now, in this particular triangle here, when you draw a perpendicular line, meaning there's a right angle or a 90-degree angle between the base and the height, when you draw this from the base to the tip of the triangle, it does happen to hit one of the vertices of the triangle. But that may not be the case all the time. Depending upon the shape of the triangle, when you draw a perpendicular from the base, and when you try to reach the highest point of the triangle, you may be outside of the triangle, okay? So the height, even though here it's completely contained within the triangle itself, this is not always the case. It really depends on what kind of triangle you're working with and how you actually define the base, or where you define the base to be, okay? But again, if you take a look at a lot of different triangles, that would take a long time to talk about. So we're just going to use this example here. So in this particular example, here we have a triangle, and suppose we want to know the area inside of this triangle. Well, what we could do is, let me see if I could draw a rectangle here. So if I draw a rectangle around this triangle, let's say here. Okay, so that looks like a fine rectangle. Now, what I want you to notice here is that if we take a look at this triangle here, and okay, so from this line over here, so let me just color this in here. So if we look at this triangle here, forget about the right side, and we flip it upside down, we see, well, this triangle up here is really this triangle flipped upside down. And this triangle here is really this triangle flipped upside down. So by drawing a rectangle around it, what I really did was I doubled the space here. Like, you have a certain amount of space in this triangle here. When you draw a rectangle around it, you're doubling that space, because now we have this space in here and we have this space in here. So we know that the area of this larger rectangle here would be the length times the width, right? But in this case, the length here is called B, right? This base of the triangle here is B. And the width, well, that would be the distance from the bottom of the rectangle to the top of the rectangle, which in this case is H. So base times height. Now, that's the area of the rectangle, but the area of this triangle is really only half of that. Okay, so if I take half of the base times the height, that gives me the area of this triangle. Now, that's one way to see the area of a triangle. There's a lot of different ways. You could cut pieces off the triangle and glue them to other parts, and you could see that, well, you may obtain a parallelogram, but we didn't get to those yet. So let's just stick with this here. We find that the area of the triangle is 1/2 base times the height. Okay, now moving on, let's take a look at, oops, where'd we go? Okay, so let's take a look at the parallelograms. Now, once we know that the area of a triangle is 1/2 base times the height, we could use that to find the area of a parallelogram. So a parallelogram, what is this? It looks like a rectangle, but it's skewed, right, to the right a little bit, or it could go the other way to the left. But the idea here is that this top portion here is the same distance as this bottom portion here, and they are parallel. So these lines will never touch, no matter how long you extend those lines. And the same with these two sides here, this slanted side here and this slanted side here. These are also both parallel lines, and they are the same distance. Okay, so that's a parallelogram. Now, if we draw in a diagonal, let me see if I can draw a better diagonal. If we draw a diagonal from one corner to the other corner, okay, and then I drop a line here, okay. Well, let me get rid of that. First, we see that what we have here, we have a triangle here, and we have the same triangle up here. It's just flipped upside down. So this parallelogram consists of two triangles. Now, the area of this triangle, if this is the height here, this is the base. Okay, so the area is going to be the area of this triangle, which is 1/2 base times height, or b times h, and then the area of this triangle, okay, which has the same height and has the same base, so the area of that triangle is 1/2 base times height. So when we add half base times height plus half base times height, we're going to get just base times height, because 1/2 plus 1/2 is 1, and then base times height. Okay, so when we see a parallelogram, if we know the vertical distance from one piece, or one vertex drop down here, that's going to be the height. And if we know the distance from here to here, which is the base, then if we do base times the height, we're going to get the area of this parallelogram. Now, it's important to keep in mind that this, if you had this distance here, the diagonal distance, that's depending on the type of problem, that's not too relevant. It depends on the information given, but you want to be careful not to mistake this diagonal portion here as being the height. Okay, the height is going to be the vertical distance from one base to the other base. Okay, so that's the area of a parallelogram. And now we have a trapezoid here. So trapezoids, they come in many different shapes and sizes as well. This is one particular instance of a trapezoid. So one way to find the area of a trapezoid is, if you wanted to, you can cut off this triangle here, flip it upside down, and place it right over here. Okay, that's one way to find the area of a trapezoid, because what we then have is we have a rectangle, and we know how to find the area of a rectangle. So that's one way to find the trapezoid. Or we can make a complete copy of this trapezoid here, and what we're going to do is we are going to flip it and place it. Alright, so we're going to flip it and place it along the side here. Okay. So I'm going to call this base 1. The distance from here to here is base 1. The distance from here to here will be base 2. And if I flip it and put it over here, then this top portion in the yellow here, that will be base 1. And the distance from here to here, I didn't draw it too accurately, but that should be base 2. Okay, so I made a copy and I flipped it and I put it over here. So essentially what that did was it doubled the area, right? But now, and what's this here? That is called H. Okay, so I have this shape here. This new shape that I created is a parallelogram, right? And we know that the area of a parallelogram was going to be the height times the base, right? So in this case, the area of the big portion would be base 1 plus base 2, By the way, you would read this as B sub 1 and B sub 2. These are considered to be subscripts. Okay, so the base is B1 plus B2. Now, we would multiply this by the height. Okay, so that's the area of the large figure here. However, to create that large figure, I had to double the area of this. Okay, now we just want the area of the trapezoid, and that should be exactly half of that larger figure. So the area of the trapezoid is going to be 1/2 base 1 plus base 2 times the height. Okay, and that's one way to find the area of a trapezoid. Now again, the trapezoids come in a few different shapes and sizes, so you may see different ways to find the areas depending upon what the trapezoid looks like. Moving on to the last shape here, we have a circle. So a circle is all the points in the plane that are a given distance from a point called the center. So here I have the center point. The distance from the center to the outer edge of the circle is called the radius. Okay. If you drew a line from one edge of the circle through the center to the other edge of the circle, that's going to be called the diameter. The radius is exactly 1/2 of the diameter. So with the circle, we want to find the perimeter, which is called the circumference in this case, and then we also want to find the area of the circle. So let's talk about the circumference. Okay. That's not an A. Circumference, that's an E. Okay, even though this is math, I still try to spell the things correctly here. So circumference. So the circumference, there's a formula for this here. It's 2 times pi times the radius, where pi is a constant number. Now, how did this come about? Well, one way to see how this comes about, may take a while, but if we draw some figures here, I think this is called the method of exhaustion. Draw a straight line here, that's easy to measure. Draw another straight line there, that's easy to measure. Actually, let me go like this. Draw another straight line here. Trying to go along the outside. Okay, another straight line here. Another straight line, and so forth. Okay, and lastly, one more line. So that, if we measure the outer edge of the circle like this with all these straight lines here, let me get rid of this. You could also do the same with the center of the circle. We go like this, we stop here, we stop here, stop here, and then we go like this, cut across. So these straight lines are easy to measure. Like we could have that distance here. And the circumference of the circle in this case would be, considered to be between the perimeter of the outer edge and the perimeter of the perimeter of the outer figure and the perimeter of the inner figure. And if you make smaller and smaller lines, you're going to get more accurate representations of what the circumference is. And pi was estimated like this to be, very close to what we know it is now. But we just use the symbol pi here because pi is a transcendental number, meaning it's an infinite decimal with no repeating patterns within it. So we could never fully write it out if we wanted to. It would take forever to do. So we just use the symbol pi here. Pi is approximately 3.14159 and so forth. Okay, so the circumference is 2 times pi times r. Now, this is the perimeter of the circle, and again, that's a one-dimensional measure. Now, the area of the circle is pi times r squared. Okay, now remember what I said about being a two-dimensional measure. In this case, when we have the area, pi times r squared, we have this squared in here. And that's going to tell us that this here is a two-dimensional measure. That's the space inside of the circle. Okay. Now, you may mess up the formulas here between circumference and area. What you really need to pay attention to is the fact that there's a 2, there's a pi, and then there's the radius of the circle. Okay, here's a 2, a pi, and again, we have the radius of the circle. So if you forget where the 2, the pi, and the r go, you just need to recall that circumference is a one-dimensional measure, meaning everything here is going to be to the first power. All right, so we shouldn't really see any powers. If everything is to the first power, then the 2, the pi, and the r are just going to be written next to each other. In the case of the area, if you know that area is a two-dimensional measure, you want to think, okay, that means there's going to be a squared somewhere throughout here. Okay, in my units anyway. So there's going to be units on the radius, and these units are going to end up being squared. So if you know that area is a two-dimensional measure, you should remember that the 2 is going to be the exponent of the radius. Okay, so that's one way to remember the difference in the formulas between circumference and area. So we have 3 examples here to take a look at. So let's take a look at the first example. So we want to be able to find the perimeter and area of a triangle. So in this case, I have a triangle here with some units on here. Now the perimeter, it doesn't matter what figure you're dealing with, it's always going to be the distance along the outside edge of the figure. So we have 12.6 feet. Now let me drop the units for now while I'm doing the math here. So 12.6 plus 5 plus 10.4. Okay, so 12.6 plus 5 is going to be 17.6, and then 17.6 plus 10.4 is going to be 28, and the units are going to be feet. Okay, so recall, again, perimeter is going to be a one-dimensional measure. My units are going to be to the first power. Now, in the case of the area of a triangle, let me just do a little try there, just to show that I'm talking about a triangle. It doesn't matter, though. If the picture is a triangle and you tell me the area, I know you're talking about a triangle. So the area of the triangle is going to be 1/2 the base times the height. So this is going to be 1/2. Now the base is 12.6, and the height is 4. Okay, and I'm just dropping the units for now just to do the math. I know the units are going to come out to be feet squared or square feet. So one way to do this, if you didn't want to use the calculator, 1/2 times 4 is 2, and 2 times 12.6 is going to be 25.2. And the units are going to come out to be squared feet. Now, why did it come out to be squared feet? Well, if I actually wrote my units in, this is 12.6 feet times 4 feet. So the feet times feet give me the squared feet. Okay, so that's the perimeter and area of that triangle. Moving on to example number 2. We have that the length of a rectangle is 10 more than twice its width. The width of the rectangle is 50 yards, so we want to find the perimeter and area of this figure. So here's a word problem. With some word problems, it's going to be helpful to draw a figure. Now you don't need to, but even for me, it'd be easier to see the rectangle that they're talking about. So we're talking about a rectangle here. So let me go ahead and draw a rectangle. Oops. Okay, and left side. Okay, so there's a rectangle. Now we have the length and we have the width. So they tell us that the width of the rectangle is 50 yards, right? So they go ahead and give us this side here. Now this side is also the width, so I know this is 50 as well. Now what do they tell us about the length? So when they say the length of a rectangle is, so this is translates to an equal sign. Okay, so length is means length is equal to, and then 10 more than twice its width. Okay, so this piece here, twice the width, is 2W. And then 10 more than twice the width means you would take this quantity and add 10. So this reads the length is 10 more than twice the width. Okay. So I know that the width is 50, so this is going to be 2 times 50 plus 10. So 2 times 50 is 100. Adding 10, so 100 plus 10, we get 110. Now, what are the units on here? We're talking yards, right? So this is going to be 50 yards, and this is going to be 110 yards. Okay, so 110 yards. So now I have a nice picture. I know the sides of my rectangle, and I could go ahead and now and find the perimeter and the area. So the perimeter is, again, the distance along the outside of the figure, so 110 plus 50 plus 110 plus 50. So this is 160, and 160 plus 110, we'd get 270, and 270 plus 50, we're going to get 320. Now the units on there, since this is one-dimensional, is just going to be yards. Now the area, the space within this rectangle, is the length times the width, which in this case would be 110. I could write the units in just for now. So 110 yards times 50 yards. So 110 times 50. Well, 50 times 100 is going to be 5,000. And 50 times 10 is 500. So we're going to get 5,500 squared yards. Okay, so 5,500 squared yards is the area of this rectangle here. Okay, and last up, let's take a look at example number 3. So in example number 3, we want to find the area of the shaded region. Okay, so the shaded region here is where I drew all these lines here. Now we have two circles. We have this outer circle and we have this inner circle. Now, first of all, find the area of the shaded region. We're talking about the area of a circle. So our choices for our circle formulas are 2 times pi times r, or pi times r squared. Now remember, area is a two-dimensional measure, so we're going to have a pi, we'll have an r, and we have a 2. So the 2 should be the squared because, again, it's the two-dimensional measure. So area is pi r squared. Now, let's see. So the area of the shaded region. Well, we could find the area of the bigger circle, and if we were to subtract the area of the smaller circle, then that's going to leave us with this area of the shaded region. Okay. So area, I'm going to call this A sub B, so the area of the bigger circle minus the area of the smaller circle, I'll call that S, will give me the area that I want. Okay, so now the area of the bigger circle, now you could write out a formula like this if you want, or you could just do the work separately, and then at the end you could subtract them, or subtract the smaller circle from the bigger circle. So the area of the bigger circle is going to be pi. Now what's the radius of the bigger circle? Well, we have that. The radius is 24. So pi times 24 squared. And in this case, we have 24 squared. And let's see. So if you have a calculator handy, you could find out what that is. We see that it's 576. And then we have pi. And the units are squared feet. Now, when we have a pi involved in a calculation, typically it's best to leave the symbol for pi in there. Because if you estimate pi to be 3.14, you're going to obtain an inexact answer. Whereas when we say something like 576 pi, this is an exact answer. So this is most definitely preferred than using the estimation of pi as 3.14. So it's really preferred that you leave your answer in this form here. Okay, so the area of the bigger circle, we get this. Also, just as a brief note, we have to follow the order of operations again in this particular case. So parentheses would come first, but there's nothing to do in the parentheses. After would be exponentiation, so that's why we do 24 squared to get 576, and then we multiply it by pi. Okay, so just keep that in mind. Again, we'll go over that in a future video. Next up, the area of the smaller circle. Well, the smaller circle has a radius of 20, right? So pi times r squared would be pi times 20 squared. And this is going to be 400 pi. And our units on there are squared feet. So now, if I take the smaller circle, if I take the area of the smaller circle and I subtract it from the area of the larger circle, so 576 minus 400, this is going to equal 176, and the units on there, again, are squared feet. Okay? So 176 squared feet is the area of the shaded region. So that's it for this particular video on the perimeter and area. Hope you enjoyed it, and I'll see you in the next one.